this computer. Okay, good. We got that. Now I can share, and hopefully everybody can see the slide.
Yes, all two of us.
Okay, and then let me enter full screen. There we go. And hopefully this looks relatively easy. Okay, so we're finally gonna get to the end of where we actually get a solution to the Thomas Fermi equation. And we're gonna do a slight review of some of the material we've done before, but hopefully there's a few additional things that will be interesting. Anyway, get this page down. Okay, good. So we're going to touch a lot of stuff here. And as I've said before, this is the only picture I've ever been able to find of Llewellyn Thomas, who was the Thomas of Thomas Fermi. We've seen Fermi before many times, I'm sure. So we've been looking at solving ODEs using perturbation theory. And when I tried to use it on the Thomas Fermi equation, getting one or two of those turned out to be pretty easy, but it was a real pain in the butt trying to get even a third term. So I decided, all right, I'll look at collocation and quasi-linearization. So anyway, we've talked about classical polynomial vector spaces. So you need an inner product, and if you use integral from -1 to 1, vector G, then you find that x to the n is not orthogonal, but you can do the Gram-Schmidt process. And Richard Bellman's book, Introduction to Matrix Analysis, is a really good one. And that book is actually quite useful. So if you can find a copy of it, I would recommend it to your library. Anyway, so we revisited Gaussian quadrature, and the idea is basically that if you choose an appropriate set of points, which are specially chosen, and Gauss figured this out originally in 1856, I think, or something like that. No, 1817. Anyway, yeah, 1786, something like around there. Anyway, and like I said last time, I got an English translation of his paper, and it was, for me, almost impossible to read. So eventually, Carl Jacobi in 1826 did what we do today using the regular numerical analysis work that we do. First thing you need is to have some kind of an inner product. Once you have an inner product over some region and a weight function, you can get orthogonal polynomials equivalent to that. And what Gauss and Jacobi showed was that normally when you do all kinds of numerical integration, if you use endpoints, the most number of terms in the Taylor polynomial that you can integrate exactly is of degree n. But by especially choosing these points x of I and the w sub I, you can make them 2n minus 1. And there's another guy called Conrad who found that if you added another n points in, then and corresponding weights, you could actually make it 3n minus 1. So people keep trying to get better and better with fewer points. Okay. Why were we doing this? Well, we were trying to solve a nonlinear ordinary differential equation. And we talked about Larkin and his way of doing it. And if you have a nonlinear differential equation, f of y, y prime, y double prime, equals some function g of x. And you can put the g of x in the function and just make it equal to 0. Over some region AB. And he was particularly choosing functions that had boundary conditions, that is, using 2-point boundary value problems. Anyway, the idea is you choose a set of basis functions, and then you approximate these are basically just Fourier series with different versions of basis functions. You do a constant number of a subspace of the infinite dimensional Hilbert space that is the basis of Fourier series, and you choose a finite subspace, and then the idea is you take this ordinary differential equation and you want to take the approximation function with unknown constants, c sub 1 through c sub n, stick them into that differential equation, and integrate it from the region AB that it's defined over. And then you can do various things. The thing that Galerkin noticed is that you can project it from whatever the residuals are onto the subspace, and that makes it an easier problem. The other one is to just take the objective and find the do a minimization of that and get the C's that way. So either way works, they're equivalent. Oops, sorry. Okay. The problem is that the integral, even doing it numerically, can be a lot of work. So the idea is to simplify that integral, the integral from a to b of f minus g squared. Do that using Gaussian quadrature. So here's the Thomas-Fermi equation, which we've seen numerous times. And it is pretty nonlinear. And it's got various forms of boundary conditions. The one that I've been working on is y of 0 equals 1 and y of infinity equals 0. And we had we had two initial solutions, one by Fermi and one for Sommerfeld. Fermi's was good for about 0 to 0.1, and Sommerfeld's was good from 100 to infinity. So the question is, what do you do in between those?
Bob?
Yeah.
Just real quick, very simple question. Okay, so you're saying this is the equation for a neutral atom. So what is y? Y is
Oh, it's a charge density.
it's a charge density. Okay.
It's a charge density for the atom.
Okay. So and that's that and the atom is at Y equals 0
It's
or
at the center.
it's at X equals 0.
X equals 0 is the center of the atom.
And the atom has no finite size.
No, it goes to infinity. Well, the charge
Goes to infinity, but the atom has no size.
Right.
Got it. Okay, thank you.
Okay. Anyway, okay. And this is non-dimensionalized, doesn't have charge units. This integrates to 1, whatever the number of charges on the atom are. Just multiply by the number of charges to get the charge density. Okay, so we talked before about the Sommerfeld equation, and he noticed that that equation has a particular solution, 144 over x to the cubed. Unfortunately, although that works quite well for x goes to infinity, it doesn't come anywhere close for x equals 0, because obviously it goes to infinity. So he mucked around with that particular solution and came up with this solution. You take the particular solution and you have 1 plus that particular solution to 1 value of lambda divided by 3 and and the whole thing by lambda, the second lambda divided by 2. Anyway, like I said, that particular solution also has y of 0 equals 1, but it's not monotonically decreasing. It goes to hell around 0. Anyway, so it's very useful for x greater than 100. And I used a couple of various perturbation solutions on the Thomas Fermi equation. The first perturbation solution didn't even satisfy the boundary conditions, therefore we did a second one. And this one was where you take 3 to the halves by taking 1 plus epsilon goes to a half. And the square root of x is 1 minus epsilon. So you can do a solution for this for epsilon equals 0. And it gives you a k-Bessel function times the square root of t and an I-Bessel function. I-Bessel functions are a bad thing. They go to infinity as c goes to infinity, so obviously you throw that term out. And this has the proper infinite limit. As t goes to infinity, it goes to 0. So maybe I could use this for a collocation version of that equation. So if you look at, you need to have it start out at y equals 1. So if you look at all of these equations, you'll see that they do have, you can have a line y equals 1, and you can just shift each one to various places, and you'll be able to get something that starts at 1 and the limit goes to infinity. So those will match the boundary conditions, which is what you need for the Lurkin method. So finding those particular shifts gives something that looks like this. The Gaussian stuff, we've talked about this before. You need the n, in order to get the weights, you need both the n and the n plus 1 orthogonal polynomial. And you need to know, if you know the roots, t sub I, of those polynomials, then, or or actually just be event, then you can write it in the form of the product of x minus each one, but there'll also be a coefficient in front of it. So you need to know that as well. And so for the W sub i's, it's the ratio of the k's 1 over the derivative of the n times the polynomial of n plus 1. Each one is evaluated at the root of p sub n, t sub 1, t sub 2, to t sub n. So that's the procedure for the weight. So the first thing you need to do is choose a set of orthogonal polynomials. And there seem to be fairly 3 possibilities. 1 over square root of x, because we have y to the third over square root of x, so that might be a reasonable one. 1 over x, the way in which I did the perturbation theory, it turns out to be x. And then the third one was based on some stuff that was actually proposed by Fermi, because 1 over 1 plus e to the x works from 0 to infinity. So he wasn't trying to match Sommerfeld equation. He was just doing it over the whole thing. Okay. We looked at Galerkin before. He was in the Russian Empire, 1871. Like most people in Russia, he spent some time in prison. His first scientific publication was done while in prison, but the one that everybody is really interested in is the 1950 paper publication, which showed the one that we're using, the approximate method for differential equations. And there's various versions to do it. I'm doing it for differential equations. You don't need weak solutions for differential equations, but you do need them for partial differential equations. Anyway, they're used a lot. So how does it work? You need some kind of Fourier series, so you need a countably infinite bases, that is an infinite Hilbert space. You've got a nonlinear differential equation, which I took the g of x and put it in all the whole thing. Theta. Then you choose a finite subspace. Assume that the solution to the differential equation is in the Hilbert space. Approximate it as a ray in the subspace. Determine all the residuals and orthogonally project the residuals onto the subspace. So we looked at a couple of examples. We took a differential equation that is equivalent to 1 minus x cubed. And for ordinary Fourier series, it did not work very well at all. But if you choose Bessel 0 and you take a look at all of the infinite zeros of the Bessel function, you can choose a finite number of them. And if you do that, then Bessel of x of Bessel 0 of 0 is 1. So that's one of the conditions that you need. And for each alpha sub I times x, when x is 1, since it's a 0 of j, that's going to give you a 0. So those are, they satisfy the condition that Galerkin said, you have a 2-point boundary value problem. You need to have the proper boundary conditions in the basis functions. So here's what the bases look like. First one, the blue one, just goes directly to 0. And the orange one is the second one, and they keep getting more and more oscillations around there. But here's our differential equation. 1 minus x cubed is equivalent to a linear ordinary differential equation, a 2-point boundary value problem. So minus 2x squared over 3 u double dot plus x u prime plus u equals 1. And as I said, the boundary conditions u equals 0 equals 1 and u equals 1 are chosen to dissolve to make sure that all of those boundary conditions match. So if you do this with with an infinite number of terms, it will obviously, like all Fourier series, get correct. But if you do 5 terms, then it does pretty damn well. You can see they're not quite exactly the same, but they're pretty close. So what I did was to take a look at what happens when you start at 5 and you keep adding more terms. And you see that the integral from 0 to 1 of the approximation with 5 is about, 4 times 10 to the minus 3. And it halves and it halves, but it doesn't have. So it goes down, but it doesn't go down real fast, which I hadn't realized. Okay. So the question is, it does work, and you can add enough terms to make it work. Obviously, 25 is pretty good, but you might want to do better than that. Okay. So here's the log of the Galerkin RMS error as the number of terms. You can see they start out at, like I said, 5 times 10 to the minus 3. But if after 25 terms, it's still only 1 times 10 to the minus 4. Only got, one extra power of 10. Really. So we're going to use all of these tricks to solve the Thomas-Fermi equation. We use Gaussian quadrature to approximate an integral. We're going to choose a set of basis functions. We're going to use Galerkin's method for an initial condition. And then we're going to use a new term that I don't think I've talked about, which is quasi-linearization. And that's going to get us to where we want to go. So if you use the 5-term, which one is this? Oh no, this is the Thomas-Fermi. Sorry, it should be TF, not FD. TF equation. So I had this original approximation where I have used these various Bessel functions, and I found a linear combination of those using Galerkin's method, and it looks fairly good. It starts at 1, goes to 0. It's monotonic, decreasing, all those good things. But if you, and it does, like I said, it monotonically decreases logarithmically. You can see that quite easy. But how good is the Galerkin approximation using those Bessel functions? Well, you can write a residual. So we have square root of x, y double prime, minus y of x to 3 halves. We've got the boundary condition, so that's not a problem. And we want to take that residual over the integral, either 0 to 100 or 0 to infinity, and then figure out what the coefficients were. And I did that first step. But how good is that residual for the ordinary differential equation? So if you take a look, you see that it from about 2 on, x equals 2, it's pretty good. It goes down to almost, the square root of the integral over. This is showing it without the integration, but just to show you where the problem is. The problem is that the linear spaces have 4 derivatives, and when you do Galerkin's method, you don't come close to matching the derivative of the Thomas-Fermi equation, which is 1.58807102226, ... So you see, that's where the problem is. All of the differential equation has problems because the derivative doesn't work very well. So another couple of people, Kantorovich and Bellman. I don't think we talked about Kantorovich and Bellman last time, did we?
No.
Okay.
Hey, Bob, one comment.
Yeah.
You keep kind of fading out, like you're moving away from your mic, and if you're recording this, you might want to adjust that.
Okay.
You can still be heard, but you get less loud.
Okay. Hopefully this is better.
Yeah, probably, yes.
I moved it closer to me. So, all right. So, 2 interesting guys, Kantorovich and Bellman. Richard Bellman was born in 1920 in New York City, and he was of Polish-Russian descent, non-practicing Jewish parents who ran a small grocery store in Brooklyn. He was an atheist. He attended the Abraham Lincoln High School in 1937 and studied mathematics at Brooklyn College. And he got a BA in 1941. During World War II, he worked for the Theoretical Physics Division Group in Los Alamos. He was a colleague of Feynman and all of the others were there. And he later got after World War II, he earned an MA from the University of Wisconsin. And then in 1946, he received his PhD at Princeton under Solomon Leshitz. In 1943, he didn't go academic. He worked for many years at the Rand Corporation. And it was during this time when he was at the Rand Corporation that he developed dynamic programming, quasi-linearization, inequalities, and various kinds of programming. And dynamic programming was this insight that if you, instead of just looked for a global optimization, some global minimum of an optimization, you could do considerably better by doing a sequence of solutions which were where the next one was conditioned on the previous one, whichever one turned out to be good previous. So it was a stepwise procedure and just changed control theory completely. So in between the 60s and 80s, he was awarded several prizes, the IEEE Medal of Honor, John von Neumann Theory Prize, Principia Cybernetica gave him a Systems Science Prize, the American Automatic Control Council awarded the Richard E. Bellman Control Heritage Award in 1979, which they've continued to get award each year since then in 1979. Anyway, his biggest insights were basically in control theory. Okay. Leonid Vitalyevich Kantorovich, 1912 to 1986. He was a Soviet mathematician and economist. And his theory and development of techniques for optimal allocation of resources is what he is most known about. People didn't know it. He actually, in 1939, developed linear programming long before Danzig reinvented it in 1952, I think, 56, somewhere in that period of time. Anyway, he worked under Stalin. He did most of the work for allocating all of the resources in Russia for several decades. And in addition to the Nobel Prize in 1941, he was given a Nobel Prize in economic sciences in 1975. His work on functional analysis, which he started in, I think it was 48, something like that. Anyway, maybe it was 52. Anyway, turns out that he'd beaten Bellman's quasi-linearization and many other things that Bellman produced. So he was very prolific. Like I say, he developed linear programming long before Danzig, and all of the weak solution methods for Krylov methods that are the big rage today for nonlinear ordinary differentials, partial differential equations, integral equations, etc. He developed all of that in the 50s. The problem with Russian, he did all his publication in Russian journals. And the CIA started translating Russian journals in the late 50s, 54, 56, somewhere around there. And his work on functional analysis was actually translated by the CIA in, I think, 58. Anyway, but Bellman was completely unaware of it. And later in the 60s, he found out about it. And once he was aware of Kantorovich's work, he always noted the precedence of Kantorovich's work to his work. So you can read his early papers and then you can read his later papers, and he always includes Kantorovich in his papers. So does anybody know how linear programming works and how Danzig found it?
Not I.
Okay.
Well, I know I kind of know how it works, but I don't know how Danzig found it. So
well, he was a student at Princeton, and he had a 8 a.m. math class, and he found it was very hard for him to get up and get there for an 8 o'clock class. So one day he showed up about 8:30, 8:40, and of course, the class had been going on for more than a half an hour, and he noticed on the left-hand board there were two problems, looked like problems to him. He thought they were homework problems. So he wrote them down. And by the time he got back to the next class, he had solved them. Unfortunately, they weren't homework problems. They were open problems that nobody had solved up to that point. And the teacher had just wanted to let people know about these, and they do really good work if they get a lot of important results if they had ever figured out how to do this. But Danzig just thought it was a homework problem, so he solved it. Anyway, so what is linear programming? You have a linear function, some vector of constants times a set of what are called decision variables. The x's are called decision variables. They're the things you're trying to solve for. And they've got a subject, a set of linear constraints. So some matrix A times X equals B. Now, it turns out you really don't need to use the equal sign. You can do a mixture of greater than or equal to and less than or equal to. In order to change it into an equal sign, you add some more variables called slack variables. Add them in, then you've got the expanded set X and the slack variables, and then they turn out to be equal. So people always write it this way, but that's not really true. You can use any combination of greater than or equal, or less than or equal to, or equal that you want. Now, the thing is, you're trying to allocate some sum of the x's, and you don't want to have that are equal to some constraint, and you don't want to have negative x's. So linear programming and many other types of programming are done in what's called a positive orthont. If you think about a three-dimensional Euclidean space, there's, x positive, y positive, z positive. Okay, that's one. And you can have x positive, y positive, z negative. That's another orthont. If you have x negative, y negative, that's another one. So you can cut up the infinite cube of Euclidean space and make it in three space, and you'll get 8 pieces, which is why they're called an orthont. Unfortunately, if it's done in n dimensions, it's still called an orthont. I don't know why, but I guess mathematicians are lazy. So the limitation is, regardless of what the dimension is, the x's are always positive, and that's the non-negative orthont. Okay, so there's something you can do for every inequality. You can, if you have a inequality on a set of variables, there's a plane that splits the Euclidean space of that dimension. And for one side, it'll be what's called a half space. And on the other side, it's not part of the solution. So the side of the space, so you find a plane that cuts the Rn, and the side where it's true, that's where the inequality is satisfied. That's called the half space, and the rest of it is where you don't want it to be. So in general, you have a finitely many number of linear inequality equations, and you have all of these half spaces. If you intersect all of those, you'll get what's called either a polyhedron or a polytope. Both names are generally uses. If the polyhedron is bounded, it's called a polytope. Okay. So the idea is you look at the positive orthont, take all of the half spaces, and you'll find a polyhedron in that. And then you look at the linear objective CT and add all of those at the polyhedron. And it turns out that all of the extrema of that polytope correspond to the possible places that you could have solutions to the minimize the linear objective. So the way linear programming works is you build this polyhedron or polytope, and then you find a region where there are solutions that some set of objectives are satisfied, and those are a finite number of points. Those are called the feasibility region. You choose the one that is the lowest of all of those points. points, and then you start climbing up the polytope until you find the lowest one. And I'll show a picture of that shortly. One of the things that's really interesting about it is that there's a dual problem. As just like every Euclidean space, you can look at the row vector space as being equivalent to the dual, which is the column space vectors. So you can have a maximize the, in this case, the inequalities are P. So you use the inequalities to maximize a different set of decision variables. You take the transpose to that matrix, and those are less than or equal to the coefficients that are used in the objective in the linear. And the y's are also a positive ortho. So it's, you're again just optimizing a linear function over a polyhedron. So you climb up the polyhedron until you find the one that's largest. So you can do a maximum problem or you can do a min. They both work. They do the same way. So here's a simple example. Suppose we have an objective 3/2 minus x minus y minus z. And the 3/2 is just so I don't have negative numbers every place. Anyway, and we have a whole bunch of inequality. X is going to be greater than 1/10. Y is going to be greater than 1/5. Z is going to be greater than 1/20. X is going to be less than a half. Y is going to be less than a half. And Z is going to be less than 2/3. And 2x plus y plus z is going to be less than or equal to 3/2. And x plus 3y plus 2z is less than or equal to 2. So, got there 1, 2, 3, 4, 5, 6, 7, 8. Got 8 inequalities in 3 decision variables, x, y, and z. And this, so it's a 3-dimensional space, R3. And our x, y, and z are in the positive orthon of that. So that's the problem we're going to take a look at. So the first step in the process is to convert each of the inequalities to half spaces. Then you want to intersect all the half spaces to create a point. Determine the feasibility region and find a minimum objective over that feasibility region. And then start to climb up the polytope. Now that's not the way you program it, but you can think about it that way. It's equivalent. So here's the positive orthont. We have x, y, and z. And the region x goes from 0 to infinity, y goes from 0 to infinity, z goes from 0 to infinity, and I think I screwed that up because it looks like the game minus 1 instead of 0. But anyway. So, whoops, where'd that go? Where's my example? Oh no. I seem to have lost my whole example. Oh. Ah. I have a whole set of slides that show. Can we take a break? I'm going to try and see if I can find what I did to the slides and correct them if I can do that.
It's a good time for a break.
Okay. Sorry, I don't know what the hell I did. All
And
right.
are you going to leave your recording on?
Oh, no, I'm gonna shut it off. Sorry. Thanks.
So I'll come back in a couple minutes here.
Yeah, yeah. Stop share, stop recording video. Where's stop recording? Okay. And share and back that. Share. Okay, now let me see if I can view it in full screen. In full screen. All right. So, okay. One, sorry, you can see we have the objectives and the inequalities and those steps that we're going to do conceptually.
We're at the very beginning of your presentation. That's what we're looking at, the first slide.
That you should not see that.
We're seeing there's just that Thomas Fermi physics, that first slide.
That's very weird, right? Let's go back to there. Select it. Can you see the contents?
Well, off to the left, I'm not sure which screen you're sharing right now, because again, it's the very first slide. Off to the left is like, looks like, no, all tools is off to the left. That's the screen we're looking at.
Okay, let me try a different share. Okay, so that's weird. All right, do you see a full screen here? Got the first one, the type contents, got all that stuff.
Yeah, now you're at contents.
Okay, good. So let me move back on to all the stuff we've done already. And here's the example. So,
Okay, we haven't seen this
Yeah,
before.
yeah. This is your design space or your variable space or whatever you want to call it.
yeah, it looks like it's a little too big for me to be able to
It's
jump
shaved.
with it.
It's shaved.
Sorry, I'm gonna
Right.
have to. I'm gonna have to quit again, and I'm gonna have to do the size different uh, in tech in order to get it done properly.
Sure.
I apologize. I don't know why I didn't notice that before. Okay, quit that. Let's go back to tech. All right, where's my screen? Where's my? Okay, so let's make it 4:7. Okay.
Jack, or if you're just standing there.
That's still too big. Let's cut it down again. Let's make that 3-7. Try that again. Oh, what did I do? Surprise me. Crazy. Okay, so that's read those. Okay, take that, and that, and that, and that, and delete that. No. Okay, so that's a little too small. So what did we do? We got 3-7. Let's make it 4-2. Sorry, this is the kind of stuff that you should not have to deal with. Okay. I need it slightly larger than that. So let's do it for 4. Oh, come on. 4-6. It was at 4-7 and you didn't like it. I just did this and you complained. I'm really annoyed. Oh, I'm still recording. I should stop that recording.